Well, this is the last bit, so we're going to take it a bit easier. And what we're going to do is to calculate band structures. Okay. So in principle, this is the easiest thing you can do, but we do it at the end because we wanted to move from structures to equilibrium, deformations, vibrations, and this is technically excitations, let's say, although we do it as standard band structures. So it's very simple, but conceptually it's one of the most difficult things. But we basically just look at the Comshaw eigenvalues, okay? So the idea is basically to perform a standard calculation where we get the electronic density, and then perform a new calculation where the electronic density is given now from the previous one, is set. Because of that, also the exchange and correlation potential is set. The Hartree potential is set. So basically the whole Hamiltonian is completely specified. It does not get recalculated again. And one just solves the Hamiltonian for various wave vectors and energies and finds basically the eigenvalues of an Hamiltonian. So if you had a type banding Hamiltonian given by someone, it will be a matter of finding the eigenvalues of that. So here is the same problem, essentially fixing the Hamiltonian and looking at the eigenvectors and eigenvalues. So we don't do it in self-consistency again. Okay, so we take the simplest case of silicon again. So we start from a new file. So what I would like to have is basically the executable, then the input file for silicon, and pseudo potential. Okay, so we can get them from the previous tutorials. Here, just to go faster, I'm going to copy everything like that, and of course it doesn't go. Okay, so I made a mistake. Is a scratch to sorry. This is the last day, and obviously nothing works. Okay. So it was Scratch Summer School tutorial. So now I'm gonna get my executable. Then I wanted the pseudo potential. I could get it from previous tutorials, but I'm gonna download it again. It's faster. And then this is basically the same input file we used in previous tutorials. Okay. Since I don't remember in which tutorial we used it, I'm just gonna copy paste it as it is. So that's the input file. It's a silicon calculation. This is the thing we used so far. Standard FCC lattice, optimized lattice parameters, 2 atoms, 1 species, cutoff, position. Yeah, I think that's quite okay for silicon. Positions, key points, okay. So I'm already interactive, so I started an interactive session at the beginning. So what you can do is MPI run minus number of CPUs, that, and then, okay. So this goes afterwards. All right, so that's fine. So this is basically a standard self-consistent calculation. It's exactly what we did before, okay? Now, if we want to do calculate band structures basically for specific K points in a certain path, as we've seen before, well, we need to calculate the eigenvalues at each of these wave vectors, as simple as that. So here in this output file, remember there is these things like iteration 1, iteration 2, iteration 3, which is basically converging the density in DFT. This is no longer needed. We just want the eigenvalues for the ground state density and potentials. So we don't change that anymore. So at this point, what one does is a calculation which is called non-self-consistent. It means that basically you keep what was already there and you look for the eigenvalues of that operations. So the flag that we need to use is called calculation equal bands, and that's pretty much, the name tells you already what that means. So the input file is basically identical to almost identical to what we have. I'm just gonna copy paste it and then I'll discuss it. So I call it nscf.in. It means non-self-consistent. Okay. So the only thing that has changed is this one here. Instead of SCF, we have bands. So no change there. Then, if we want to do calculation of eigenvalues for a certain number of bands, you also need to specify how many of them you want. Because for each wave vector, you have a certain number of states, a certain number of discrete states. You may want to calculate 3, 4, 5, 300, 500, whatever you like. Okay. So in this case, we are specifying 8 bands. So we know that in the valence in silicon there are 4 bands, so it will be 4 in the valence and 4 in the conduction. We could do more, but for now it's okay. So apart from this, everything else is the same. There is only one change, is in the specification of the wave vectors that we want to use. Okay, so there is a keyword here, okay, which reads 2p by a, so it's Cartesian coordinates in units, so 2 pi divided by the lattice parameter. And then there is underscore b. That's just a keyword to say I would like to calculate band structures. So if you go to the input file, so something like so if we look for the input file here and grep to b, okay. So what does it mean? So when I use this keyword, this is used for band structure plot. This means k points are in units of 2 pi over a. Then this describes what follows, and that's pretty much like this. The first number is the number of segments I want to use in my calculation. Segments. So basically bits of straight lines. These are the vertices of this segment. So I start from this point, let's say alpha alpha alpha. I go towards 0 0 0, and then I go towards 1 0 0. So these are basically the 3 points I want to connect. So you can have 500 there. I mean, so basically this is the number of vertices, and this is the 3 vertices I want to consider now. You can put as many as you want. This is the number of points between here and here. Okay, so there will be 10 separate points. So if you have that, it's basically saying maybe 1, 2, 3, 10 here, 10 here, and this is point 1, point 2, point 3. So you will do calculation for this point, this point, this point, this point, and so on. Okay. So that's pretty much it. There is nothing else that we need to know. So in this case, for the case of silicon, basically this is the L point. So actually the terminology for the points in Brillouin zone is something that was invented 100 years ago. It's not something which has to do with DFT. Every crystal has its kind of special points. You need to open books like Kittel or other crystallography books to see how they call them. In the case of silicon, the L point, the one which is in the middle of the hexagonal phases, is alpha alpha. 0 0 0, you should know what that is now. That is gamma. And then 1 0 0 in a FCC crystal is the point x. Okay, so this will be the path between L to gamma to x. So that's pretty much it. And the way to execute it is the usual way. So basically, we run we use npr run, pw.x, and so on. So let's try to do that. So I can kill. So maybe I can move this somewhere else.
Running this non-self-consistent way, should we pre-run the self-consistent?
Yes. So that's what I just did basically. So you first the self-consistent gives you the ground state electron density, from which you get the ground state Hartree potential and exchange potential. That defines completely the Kornsham Hamiltonian. Okay, at this point it becomes a problem solving Schrodinger's equations, which are completed where the Hamiltonian is defined. Okay, so this non-self-consistent input file is just to specify at which points you want to solve it. So at this point we can run this, and this time I want to run it with this input file, right? So I do that, and it does a calculation. So let's go through this calculation a bit more slowly. Yeah, I mean, these are very, very simple calculations. But it's silicon. I mean, again, with silicon, everything is easy. Sometimes these things can take, days if you're looking at. If you look in something with maybe 50 atoms, spin orbit, non-collinear magnetism, and all these things, it takes way longer than that. Right. So we are doing all examples. I mean, maybe this has to be clear. All the examples we are doing here are designed to be executed in the 1 hour or 2 hours of the hands-on session. I mean, typically it never happens that is the case in the real world. I mean, the calculation takes always longer than what you would like to.
You have to do something extra to add spin orbit coupling.
So can you?
Do you have to do like extra calculations to add spin orbit coupling?
No, you can basically that can be you can perform a calculation which already includes that. It's just more expensive. I mean, it can be done. If you look at the documentation, you will see how to do that. In some software, people add this spin orbit coupling as a perturbation.
How
Okay.
accurate? Like how good is it?
So in general, or yeah, it's pretty good. I mean, it's good. I mean, the same accuracy as the things that we discussed during the lecture course. I mean, it's there is no problem there. I mean, it's just a matter of time and effort. So I'm just rerunning the same, but piping into our output so that we can actually look at the output 1 second. So if I now look into the output, I just want to show you what changes. So basically, this is the list of points that we generated by using those flags. So it goes from this point with 10 bins to this point. Okay, from 0, 0 to alpha, 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 0, 0, 0. And then there are another 10 points leading to 1, 0, 0. Okay, so we have in total 21 points. So the code will calculate eigenvalues for the lowest 8 eigenvalues for each of those. So if you go down, this as calculation is done, you will see that there is basically no iteration. So the thing iteration number 1, 2, 3, and so on doesn't exist because there is no self-consistent solution. And at this point, you have for the first K point, okay? So these are the energies in electron volts. And this number 2, 3, 4, 5, 6, 7, 8. Okay, so you have 8 bands for this K point. For the second one, you have 1, 2, 3, 4, 5, and so on. So that's pretty much it. So now we could actually stop here and start the hands-on session. In principle, this is basically the band structure. Okay. Clearly this is a bit ugly. It's not very talkative, but that's it. So from this point onwards, it's just a matter of trying to get this data. So what one would do in principle is to say, okay, I'm going to delete bits and trying to collect this into a file to make a plot. So, okay, you can take, copy, paste into Excel or whatever you like. So since we are a bit lazy than that, so here I just prepared a little script which is a bit geeky, which does the job for us. So you can just copy and paste that. I call it extract.tcsh. So what it does basically is look at all the lines which contains eigenvalues, extract the eigenvalues, calculate the coordinate along this path automatically and place it in an output file. Okay, so if I do that, and it should give me something which is basically the coordinate on the first column and the eigenvalues. So these are the same that we've seen before for the first K point. So coordinate, and then 8 eigenvalues, coordinate, 8 eigenvalues, and so on. So this little script extract CSH is just something which goes there and picks up the eigenvalues for you one by one. Okay, it's post-processing. It has nothing to do with DFT. It's just a matter of looking at the output file and grabbing data. So at this point, we could plot that. So you can do a plot and say, okay, so here this is not in a file, so I want to pipe it maybe into a file. Then I can go to GNU plot, and so I don't know, plot buns using 1, 2, the same using 1, 3, the same using 1, and so on. Say it again.
Is there any quicker way than 1, 2, 1, 3, 1, 4, 1, 8? Is there any quicker way to write that?
Yeah, the quicker way is that somebody like me prepares a script for you where basically it's all done. But essentially, it's quicker. I mean, if it's quicker on this side, it's slower on this side. I mean, so somebody has to do it. Yeah, it's. I mean, somebody. There is still no artificial intelligence doing everything for us. I mean, so you basically. So basically, here I prepare a little thing called plot.gnuplot. So you can load it like that. And that does it for you, but somebody has to do it basically. I mean, so this is basically the result of what the simple calculation. So that's actually what I showed you this morning. So this would be the variance band up to this point. So there are 1, 2, 3, and 4, and 2 are degenerate, and then there are 4 here, out of which 2 degenerate. Okay, so this conduction.
Where's L? I went from L to L.
Hey, maybe I just got the wrong label here, probably. Yeah, this should be L actually, that was. So that's pretty much it, and that's basically a way to calculate band structures. But the bottom line is actually that this is what contains band structures. At that point, you must be creative in plotting the way you want. I mean, so the plot itself is just, you get data, you need to plot them. So typically, this script is something that, when you do this when you work on these things a lot, you basically start doing these little scripts here and there all the time. So you have a forest of scripts in your directories that you use. I mean, and a lot of these tools that people are developing as post-processing and putting into databases or repositories, it's not as simple, but versions of this where there is a little script which does operations that you would do manually. That's the same thing if you want to search a database or use some kind of database for materials to form an input file and run a calculation. The scripts, they do precisely that. They log into a website, they search for this material, they download the file in a certain format, they convert into the format needed for the code, they prepare the output, the input for the code, they submit the calculation. So it's what you would do, but it's done, recorded. It's basically, if you use things like Word or Excel, that's the equivalent of a macro. Basically, you record all the operations and they are done once and for all. You repeat them all the time. Okay, so that's basically the for band structures. Okay, so that's basically the same plot I showed you. I just colored in red the conduction. And I think if you look at that, maybe we can take a look. What you see basically is that, first of all, the top of the valence is not 0. There is no reason why it should be 0. In many codes, it's set to 0 just because it's a convention. Okay, so it's any number. So basically, this is where you find top of the valence. What is that? 6.2 more or less. So and at the bottom, the conduction is around what 6.7. So it's about alpha volt, the gap. So clearly, I mean, if you do a paper, you don't look like this eyeballing it like more or less. It's you calculate the minimum carefully, okay? But that to give you an idea, that's to give you an idea that there is an indirect gap, and it's smaller than in experiment, okay? And the direct gap instead is what it was 6.2, and this is what 8.7. Okay, 8.8. So it's well, maybe 2.6 or something like that. So it's about 0.6 smaller than in experiment. Okay, so that would be the absorption onset for a direct absorption in silicon. So that's basically a one example or calculation. And what you will be doing in the hands-on session is to do this calculation for the case of, I think, strontium titanate. I think at some point you will hate this strontium titanate, and for graphite. Okay? And then at the end there will be a calculation on, I think, on gallium arsenide if you are interested. Now let's look at another thing which can be useful. This is mostly useful for getting a bit of a feel of what wave functions look like. So it's trying to maybe visualize how a wave function, a constant wave function looks like. To do that, we need basically a little piece of software which is called pp.x. Basically, pp stands for post-processing. So this is basically a little code which is executed after a standard calculation, and you can use it to take some of the output and put in a format which can be visualized and things like that. So there are many options. So maybe I can you can take a look at the input documentation for this thing. Okay. So there are various things which are possible. Let's look at the possible operations. So you can plot something like charge density, the total potential seen by the electrons, the local potential of the ions. You can try to plot the density state at Fermi level. You can try to plot STM maps, which is basically a local density of states on a plane. You can plot the difference between spin up and spin down electron charge, which is basically the spin density. You can try to plot the square modulus of the wave functions and many other things, basically. So you can look at that and you will find all kinds of things that you may want to plot, depending on the application you are looking at. So what we will do here is just to plot essentially the square modulus of a wave function. Okay, so nothing really complicated. So to do this, we need a little. So what we need to do is to make this code. So I did it already before this session. It takes 2 minutes. It's a small thing. If you go to the Espresso directory and you type make pp, that will create a this is so juvenile. That's it. So I think for the record, you're gonna say this is from the director of Paradim, so that it stays on YouTube.
Your kids.
It's really the last day. So with the post-processing code, which we'll not call anymore, post-processing.x will actually, you can move it onto your directory, and that's fine. And the input file is this one. So I'm going to basically copy and paste, and then I'll describe it in a bit more detail, okay? So here was VI. So what you see here is just the prefix has to be the name of the the files that you use, the same prefix you use for the SCF and non-self-consistent calculations. This tells the code where to find the files. Usual things, output directories. This will be the name of the file which will contain your wave functions to visualize. Now this mysterious plot number 7 is just a flag. So if you go to the input documentation I just showed you online, you will see that this corresponds to basically the square modulus of a wave function. Okay, so you will need to go there to decide every time what you want to calculate. So this L sign is just a way to say that we just don't want only the modulus of the wave function, but also keep track of the sign. So when the function is negative, this sign is taken into account. Otherwise, if you have, for example, p orbitals, you would just have something which looks like the same sign, but by using this flag, you have plus and minus, so it's more. If it's imaginary, you cannot. Basically, this is basically you can only plot the real part. Basically, I mean, if it's imaginary, the problem is that the wave function basically depends on in which unit cell you are basically. So that's why people plot psi square. that's if you want to plot the wave function, you can only plot it basically at gamma. That's a real number. Otherwise, you would have a real and complex part. So that's so people typically plot the psi square. Then this flag is just telling me which point out of all the entire list. So for which point I want my wave function, right? So the wave function is something like psi, band, and k point. If I want to plot it, I need to tell which one is this and which one is that. So if you remember the list here, so we had this list of k points, and so I need to specify which one I want. So I'm selecting 11, which is the gamma point, 0, 0, 0. Okay? And also, we need to say which band we want. I'm specifying basically the top of the valence band because it's band number 4. All right? So it's basically, if we look at this, k point, basically k equals 0, and band number 4 is the top of the valence band at gamma. Okay? It's just a choice. You can choose anything you like. I mean, this is just something to decide one wave function to plot. So once we have that, we just use the usual prescription for executing this software. So it would be something like that. And okay. I didn't copy it. So,
Where's the output, John?
so I did not copy the. Okay. Well, I mean, if I don't put the output file there, it basically shows me the okay. So now this is done, and what I should find, basically, so the latest file which was written is this one. So this is already in a format which can be read by this XKZen. Okay. So this would be the wave function corresponding to the k point equal gamma and the band index number 4. So it's top of the valence band. So it's one wave function. Okay. So to visualize that, I need to run XKZen, and at this point, this will be slow because I'm on Edurom. But let's see whether we can get there. And so the procedure is extremely simple, but maybe it's useful to go through this once. So what we basically need to do is simply to load this file, and then play with the graphical user interface to visualize in a way that we like. So here we open this file, which has this suffix XSF. So I find it here. So this is basically the structure. And if I want to visualize the wave function, I go here, tools, data grid. Basically, it's basically data on a grid. So it's the value of the wave function at each point in the unit cell. So here, just go with OK. I don't bother that much. Hopefully we will, okay. So this is basically the main interface that we use to decide what we want to plot. So in practice, what I can do here, what is prompting me to put here is the ISO value. So you need to imagine a function in a three-dimensional volume, which is the unit cell. Well, you plot it as a surface, so you have to cut through. So if you have in 1D a function like that, you need to decide the ISO surface. Okay. So the ISO surface at this point, if you put a too large a value, you may not capture anything. So you have a wave function which is tiny. If it's too small, you get everything which is uniform. So I'm going to guess something, and then we'll see what happens. And I'm asking to render both plus and minus sign. And at this point, I get something here. So the blue is positive, and the red is negative. Okay? So that's basically what a wave function will look in the most ugly way. So if you're not happy with that, because you cannot see what is going on, you can try to, so this software can actually repeat the unit cell for you, so they can say some replicas, and maybe it's a bit clearer. So you can maybe do like that, display, unit of repetitions, modify, number of units, so maybe, I don't know, 2, 2, 2, so that's basically duplicating the cell along A1, A2, and A3. Okay. So that should give me something now. And now, what I can do here is to say that I want to expand this wave function plot to the entire file. So that's what I obtain, okay? So with the mouse, you can scroll up and down and see. And then basically that's what a wave function file would look like. And you can tell already it's not that trivial because it's not a bunch of atomic orbitals sitting on the atoms and you can really recognize quantum chemistry textbooks. So at this point, if you change these things, you would see that things can change a lot. And yeah, that's basically the story.
What kind of units is the ISO value?
So that I think is 1 over Bohr cube, basically. But I would have to.
Is that density? Is the value of density, charge density?
Is a size square, yes.
Okay, so maybe it's unit is just unit in total scale 1, right? Probability.
Yeah, but when you to do 1, you integrate the probability in a volume, so it's still always 1 over a volume.
So what I mean is that the ISO value here, does that mean is the probability density? We have first probability density to be 0.1, and this is on that part.
Yeah, so I think what he asked is what are the units of this probability density. So that's 1 over a volume, but I don't remember if this is the volume is in Bohr or it's Bohr cube or angstrom cube. But if you go to the input documentation file, you will find it. So typically, actually, the actual value doesn't matter very much. Typically, what you do is to adjust this value in order to show what you would like to show to someone. Basically, that's because it's very qualitative. It's not you can make a qualitative discussion based on that, but you cannot get numbers. Let's say out of this plot specifically. If you want to get numbers, you need to look at scalar products, matrix elements, and things like that. Okay, so that's pretty much it. And then in the hands-on session, there is a question on trying to plot the same object for graphite. Maybe I can show you. Just before you run away. So I think for graphite, it looks very pretty because it's very clear the kind of physics that comes out. So if you look near the basically at the Fermi level, near the counterpart of the Dirac cone, you get something which is quite pretty. Basically, it's a bunch of pz orbitals sitting on the carbon atoms, basically. Okay, so it's basically pz sitting on each carbon atom. So that's part of the exercises. So I think we can probably stop here for now because there's no point of pushing too much. So there is another bit in the tutorial which has to do with this thing, the absorption spectrum of gallium arsenide. Okay, so so it is a bit delicate because it involves again, like in the case of photons, several steps. So one has to calculate ground state, and then essentially one has to calculate this expression I gave you before with matrix elements and delta functions for the transitions. And it has to, since there is an integral of the Brillouin zone, it has to be done on a uniform grid. Okay, so it requires a non-self-consistent calculation on a uniform grid. And essentially, the bottom line is that the calculation is quite tricky because you cannot just use 4 points. You need to use something of the order of, I think, so here I did 30 by 30 by 30 to get something which looks like a reasonable absorption spectrum. Okay, so whenever you want to calculate this kind of properties, is no longer 2, 2, 2 or 4, 4, 4. We're talking like 50, 50, 50 or more, because really basically you need to sample very finely the parabolic dispersions and the absorption onset. Otherwise you get all kind of garbage. So just to give you an example, this is a calculation done with 30, 30, 30 for the dielectric function of gallium arsenide, the imaginary part. This is the same calculation done with, I think it's 4, 4, 4. Okay, so it's pretty much garbage. It looks like a bunch of, looks like a quantum dot basically. So it's not very good. Okay, so if you want to try that, go ahead. But what I would suggest, probably is more rewarding to try the band structure of strontium titanate and graphite and trying to plot the wave function of graphite. I think if we can do that today, it would be great. All right? So maybe we can start the hands-on session now.